In the previous two lessons, we worked with smaller polynomials to expand them into a single polynomial with a greater degree, such as x plus 1 times x plus 1, which equals x squared plus 2x plus 1. This operation brought two degree 1 polynomials into a single degree 2 polynomial. In this lesson, we'll begin to work backwards by taking a larger, higher degree polynomial and factoring it into smaller degree polynomials. The first step in this endeavor is by searching out the greatest common factor, or more commonly abbreviated to the GCF. The GCF of a number is simply its prime factorization. For example, the GCF of 18 is 2 times 3 squared, because 2 times 3 times 3 are the prime factorizations of 18. For a monomial, we do the same alongside the variables. The GCF of 10x squared is 2 times 10 times x squared. We can also find the GCF of several monomials. Let's say you wanted to find the GCF of 21x squared y and 12x cubed y squared. First, we find the prime factorizations of each. 3 times 7 times x squared times y for 21x squared y, and 2 squared times 3 times x cubed times y squared for 12x cubed y squared. Then the GCF for 21x squared y and 12x cubed y squared, 3 x squared and 1y. So we have 3x squared y. This is the common factor in each term. We can also find the common binomial between two terms. Let's say we have 4x times 3x plus 8 and 2 times 3x plus 8. Then the common binomial will be 3x plus 8. Let's work out a few examples. Number 1, 10x cubed plus 6x. Since we want to find the GCF, let's start with the smaller degree term, the 6x. We notice that 6 has a common factor with 10 and x has a common factor with x cubed. So let's rewrite the expression using the GCF. So you have 2x times 5x squared plus 3. And if you wanted to check your work, you could just simply distribute your outside component back on the inside, which would give us 10x cubed plus 6x, which is the same as our original statement. Number 2, 12x to the 2n power plus 6x to the n plus 1 power minus 3x to the n power. Here we have a very complicated looking expression. We're going to have to recall some of our exponential properties to work this one out. Let's first pull out the GCF from the coefficients. I notice that the smallest coefficient here, 3, is also the GCF, so let's factor it out. 3 times 4x to the 2n plus 2x to the n plus 1 minus x to the n. Next, we're going to look at the variables. Notice that once again, the last term has the smallest degree because the first term is double in this exponent, and the second term is 1 greater than the third term. Let's go ahead and break up the exponents. We have 3 times 4x to the n times x to the n because we have 2 n's plus 2x to the n times x because it's x to the n plus 1 minus x to the n. Now we can clearly see the GCF. 3x to the n times 4x to the n plus 2x minus 1. Number 3, x plus 3 times x plus 8 plus x plus 3 times x minus 10. Our last example has a common binomial in each term. We can recognize the x plus 3, so let's go ahead and factor it out. X plus 3 times x plus 8 plus x minus 10. Notice that we have to use braces to signify that the binomial on the outside is being multiplied or distributed to both binomials inside the braces. But we're not done yet. We can still add the two inner binomials together, giving us x plus 3 times 2x minus 2. We have one more step. After adding the inner binomials together, we are left with the binomial that has yet another GCF inside, leaving us with 2 times x plus 3 times x minus 1. It's usually standard to leave any coefficients in front of all terms, even if it was pulled from the back, as we have just done. This step in our work with polynomials was very foundational, but very important in the lessons coming up next. We needed to have a strong grasp of the GCF because it's going to be used extensively in trinomials.